Yeah, I'll talk about that more. Cool. So yeah, my name is Jay. I'm a research technician in the Caparoso lab at Northern Arizona University. I'm a little jet lagged right now, so see how this goes. But yeah, I'm going to be talking about the BIOM format mainly today, and a little bit about chime just to start things off and give some sort of context to where the BIOM format might fit into a comparative omics toolkits using chime as an example. So chime is basically a software analysis pipeline that's open source. It's pretty widely used for microbial ecology studies, and it allows researchers to take high throughput raw sequencing data from microbial communities and do demultiplexing, quality filtering, and eventually build an OTU table, which is the core data type used in chime. And once you have that OTU table, you can go ahead and do advanced downstream analyses from that table and do visualizations, et cetera. And so what the OTU table looks like, it has, on one axis, it has samples, and on the other, it has OTUs. And the data it stores are observation counts, so you can see how many times a specific OTU was viewed in a particular sample, or was seen in a particular sample. And so if you look at a very comparable table in a different tool such as MGRS, which is more for metagenomics, you can see that it also has a core data type or a core table that it deals with. And this contingency table is metagenomes by functions instead of samples by OTUs. And so even though it's representing a totally different type of data, it has that same core contingency table that's central to that piece of software. There's a number of other examples that I have up here for comparative genomics. You have genomes by ortholog groups. For metabolomics, you have samples by metabolites. And the list just goes on and on and on. But there's so many of these different comparative omics toolkits that currently exist that share this same central data type between them. And so in this chart here, you can see that in the past 10 to 12 years or so, there's been a huge jump in the number of comparative omics techniques that exist out there. And so it seems like every year there's more and more of these terms ending in ohm or omics that are being created and used in the biological sciences. And so, you know, some examples, like I've already mentioned, there's marker gene surveys, there's metagenomics, metatranscriptomics, excuse me, proteomics, and the list just goes on and on. There's more and more that are continually cropping up, and fortunately, many of them seem to share that core central data type, that contingency table that I've been talking about. So another property that's shared between many of these different comparative omics techniques is that these tables are typically very sparse, especially the larger that they get. They become more and more sparse. And by sparse, I mean that there's a huge percentage of zeros in the table itself. And so if you look at this example here, this has 100 elements in the contingency table, and only 17 of them are non-zero. And so we would say that the density of this table is 0.17. And so just to put a little perspective to this, in chime, we've seen several OTU tables, especially the larger ones, that have densities as low as 0.01. So that means that only 1% of the entries in this table are non-zero. And so these files are getting bigger, it takes up more space on the hard drive, and especially it takes up more resources when you actually try to load these tables into a program, especially if you're trying to deal with so many zeros here, which is just kind of extraneous junk data that's not very useful. And so efficiency is really going to be an issue, especially in the coming years as these tables continue to increase in size. So just for example, at the ISME meeting a few weeks ago, we did some processing for the EMP project, and the OTU table currently back then, I think it had 7,000 samples by 500,000 OTUs. And so it's just an enormous table and with an extremely low density. So to deal with these issues I just described, we present the biological observation matrix format, or the BIOM format for short. And so this was recently published in GigaScience, actually this summer, and it was developed primarily with input from the VAMPS, chime, and MGRS development groups. I'm just going to briefly talk about some of the high-level goals that the BIOM format seeks to cover. And so first and foremost, the format is designed to promote interoperability between these various comparative omics toolkits that currently exist or that might be developed in the future. And so basically the format is there to provide just a standard for storing these sample by observation contingency tables that I've been showing in my previous slides. And so by having a standard, these various toolkits will be able to communicate together and talk together transparently, because in the past users have had to do manual file format conversions. Like, so say if you're an MGRS user and you have a metagenome by function table and you want to import that into Chime, users would have to change the format around to fit it into something that Chime can understand. And so that's really error prone. It takes a lot of time to do that. And so hopefully with this BIOM format, these existing tools will be able to communicate together, and you can use the power of one tool that might not be in another to do various downstream analyses. The second goal is to allow for the efficient representation of these tables. And so like I was talking about with the sparsity issue, the BIOM format allows you to either store all of those entries that are in the table, including the zeros, or store only the non-zero values. And in that way, we've seen if you go with the sparse format, you can greatly reduce the overall size of the file when it's actually stored on disk, as well as see improvements in runtime when it's loaded into a program. Finally, the BIOM format is really tries to focus on allowing the user to add any type of metadata directly to the table or attached with the table. And so to that effect, we allow users to optionally include sample metadata or observation metadata, or a combination of both. And so this isn't enforced right now, but it really complements the existing standards. As we've heard today so far, metadata is very important, so it's probably important to keep it with your contingency table, especially with your samples. And so you could, it's foreseeable to include those minimum metadata that are described by mixes directly in the table. And so in that way, it complements those standards that exist. The BIOM format is currently based on JSON, and we mainly picked that as our data representation language over other alternatives, mainly over XML, just because it's a little more lightweight. And JSON is a very open standard. It's been used for years in web services, and there's many different parsers available in several different programming languages. So to accompany the BIOM format itself, we have an independent, standalone open source project that provides an API so that developers can hopefully start using the BIOM format as easily as possible. And so currently there's a Python API, so we have a set of Python classes that allow developers to interact with these BIOM tables. And there's also an API being put in place for the R programming language, but it hasn't officially been integrated into the full project yet. And so the real driving force behind this software project is to allow developers to submit their own implementations of the BIOM format classes in various other programming languages besides Python or R. And so to do this, we're hosting it on GitHub. I'll have the link posted up later here. But we chose GitHub just because it has a nice pull request mechanism, which allows developers to pull down the code, make their changes, and then notify the core developers of the BIOM format, hey, we wrote these classes in C++, we'd like you to take a look at them and maybe integrate them into your project if you think they're ready. And so far it's been working out really well. That's actually how the R code is being developed. It's being developed by someone who wasn't initially part of the core BIOM format development team. And so we've been going back and forth with the author, talking with him, giving him suggestions for how to improve that code before it's ready to be fully integrated into the project. We've also been using the GitHub issue tracker to sort of facilitate discussions between various development groups, especially with changes to the standard. And so I just have a screenshot up here. I made a post with just some proposed additions to the format a few weeks ago that would allow relationships to be stored between observations in the table. And so what we did was we solicited this issue tracking thread to members of the GSC as well as others in the community who aren't just part of that core development group, just to get input and see if this would be a helpful or useful change or how we could improve it. And so you can see on the right here that there's some nice discussion going back and forth between various other people trying to help me refine my idea here of an extension to the current format. So just real quick, we have a number of early adopters, namely the Earth Microbiome Project has adopted the BIOM format as a standard. And I guess as Don just said, it sounds like the BIOM format is also a standard of the GSC. When I made this slide, it was a candidate standard, so we're pretty excited about that. There's already a number of comparative omics toolkits that are using the BIOM format, either fully supporting it or partially supporting it. So chime, MGRS, and VAMPS, those are the three main ones that were involved with developing the format, and those tools already support it. And then Mother and Phyloseq, it's kind of neat to see these weren't a part of the original development group, and they've already developed support for it as well. And so it's nice to see other users starting to use this new format in their comparative omics tools. So yeah, we hope that as this format continues to grow into maturity, we can continue to refine it and get its name out there, and that it'll be really useful for allowing these various toolkits to communicate well together and transparently. So I'm not going to name everyone up here, but these were all core contributors to developing the BIOM format or the software component of the project. And I'd like to thank the different funding agencies down at the bottom here, and last but not least, the GSC for allowing me to come here and give this talk and attend the conference. I'm really enjoying myself, so thank you. I'd be happy to take any questions.